ये सब निकालेगा।
Good afternoon and greetings to all. A very warm welcome to all the participants and our resource person on the fourth day of the FDP program, Applications on Mathematical Techniques in Agriculture, Science and Technology. Today, we are privileged to have two highly distinguished academicians. A very warm welcome to all the participants and our resource person on the fourth day of the FDP program, Applications on Mathematical Techniques in Agriculture, Science and Technology. Today, we are privileged to have two highly distinguished academicians. A very warm welcome to all the participants. Sorry about the glitch. Sorry about the glitch. Continuing further, today we are privileged to have two highly distinguished academicians. Sorry about the glitch. Continuing further, today we are privileged to have two highly distinguished academicians. Give me a moment, we'll just resolve this and be back. Apologies from our part. Continuing further, today we are privileged to have two very distinguished academicians with us who will enlighten us on significant areas of mathematics and its application. Our first speaker of the day is Professor Dr. Muslim Malik, sir. Sir, have you joined?
Yes, I have joined already.
With due respect, sir, allow me a moment. I'd like to introduce you to our participants.
Sure.
Dr. Muslim Malik, Professor of Mathematics, School of Mathematics and Statistical Sciences, IIT Mandi, Himachal Pradesh. Dr. Malik has completed his PhD in mathematics from IIT Kanpur and pursued his postdoctoral research at IIC Bangalore and the University of Chile, Santiago. With more than 15 years of teaching and research experience, Sir has published over 150 research articles. Topic of today's talk that Sir will be holding is Introduction to Fractional Differential Equations and its Applications. Now, I would like to invite Professor Malik to kindly deliver his talk.
Okay, thank you. So just wait a minute, I will share this slide. Okay.
Sure, sir.
Okay, thank you. Are you able to see my slide?
Yes, sir, your slide is visible to us.
Okay, thank you. So first of all, I like to thank the organizer for inviting me in this FDP program. So especially to the Dr. Ajay Kumar. Okay, so in this talk, I will talk about the fractional differential equation first and after that I will talk about the controllability of fractional differential equation and what are the application and why we study the fractional differential equation and so on. So this is the so here question is that why we going to study the fractional calculus. Fractional calculus means here we study the derivative of order fraction. Okay, so fraction means any number which is the real number, any real number. Order will be of differential equation will be any real number. So first question about this fractional calculus was arise in 1695 when Leibniz given the formula of this nth derivative of any function f. So after this formula, L'Hospitals, he asked in a letter to the Leibniz that what will be the value of this derivative dnf over dtn if n is equal to half. So at that moment, Leibniz was not able to define this fractional derivative, but he just replied that this thing may be a very good result in the future. After that, he also tried to solve this problem, but actually he not succeeded in that. Okay, but after Leibniz in the Euler was the first person who try to find the fractional derivative of the function f. Okay, but what he did also that he find the fractional derivative of the power function only. He also not able to find the fractional derivative of the general function. Okay, so this formula is for the half derivative of x. So this is the correct formula, but he not able to find the one general formula for finding the fractional derivative of any function. So after that, there are also many more people who try to find the fractional derivative, and here so question is also that why we study the differential equation and why we study the fractional differential equation. So for the motivation behind the study of differential equation is that, so we all know that what is the meaning of differential equation means derivative. Differential operator means rate of change of the dependent variable with respect to the independent variable. So in nature, if there are any system or any model in which the dependent variable in which the which dynamics is changed with respect to time, then the dynamic system of that system can be written in the form of the mathematical model, and these models can be represented by the differential equation. That may be the initial value problem, maybe the boundary value problem. So differential equation is very important because in our real life there are the almost everything which is changing with respect to time. Hence we can find the rate of change, and if we are able to find the rate of change, then we can find the derivative, and if we can find the derivative, then the dynamics of the system we can write in the form of the differential equation. Okay, so this is the motivation behind the differential equation, why we study the differential equation. But the another question is that why we study the fractional derivative. So far, the studying the fractional derivative, there are the many real world problem, and when the engineers and scientists they try to find the solution of those models by applying the integer order derivative, then what they find that there is always some error. Okay, so they are thinking that it is maybe that if we consider this model with the help of the fractional derivative, then maybe we get better results. So actually there is the better result, and also we can see that this integral operator, integral operator are the global operator. Means integral operator we define from the on the some interval from a to t. For example, here in this equation number 1, here this is the integral of the nth integral of the function f. Okay, so this integral we taken from a to t. Okay, so this is the global operator. And what is the our differential derivative are we try to find at the particular instant. Okay, so that means they are the local operator. So there are also some theory, some area, research area where the we need the global operator. So for that research area, for example, in elasticity, we need this global operator. So for studying the elasticity model, we need the fractional derivatives. So in this way, we can see that with the fractional derivative, if we model any system with the help of the fractional derivative, then we get the better result. Also, we this fractional integral we will see in the coming lecture, in the coming slide, that they are the also global operator. So fractional derivative are also global operator due to the existence of this integral operator. So that is also very useful in study of the memory problem with memory and elasticity problem. So these are the few examples of this fractional calculus. And but also there are the some issue with the fractional calculus, because for the integer order derivative we have the physical interpretation, that what is the meaning of that. But in the fractional for the fractional derivative we not have that physical interpretation. Okay, so there are the some questions still open for all the people. Okay, so also we know that before defining the derivative of some function, we just need to know that what is the integral of that function. So with the help of that, this equation number 1, this represents the n-fold integral of the function f. So this we apply the change of variable and multiple integral, and after that we will get that in the equation number 1, this is the nth integral of the function f. And now in equation number 1, if we replace this n by the any positive real number, okay, then there is the issue is come from here factorial n minus 1, because factorial n minus 1 is not defined if n will be the positive real number. Okay, so in that case what we need to do, we need to replace this factorial by the gamma function. So gamma function also we have the gamma function in terms of the for the real numbers also. So if we replace in equation number 1 this factorial by the gamma function, then this formula will be true for all the positive real number. Okay, so in this way, so this is the motivation behind the fractional integral of order alpha. Okay, so this is called the Riemann-Liouville fractional integral of order alpha. There are also many people say the right-sided, left-sided, but maybe you can use the anyone. Okay, so this expression 2 is it is called the right-sided fractional integral of order alpha, where alpha greater than 0, alpha is any real number. Okay, and then it is 1 upon gamma. So here gamma alpha means factorial alpha minus 1. Gamma alpha means factorial n alpha minus 1. So here this 1 upon n minus n minus 1 factorial we replace by the gamma alpha. Okay, so in this way this is called the right side fractional integral of order alpha. We can see that if we just take t is equal to 0, then this will becomes the this identity operator, and this integral of the, if we take the apply the identity operator on the sum function, we get the function itself. Okay, so this is the just notation that 0 0 means number of integration we did is 0. Okay, this means function itself. Okay, so similarly, similar to the right sided integral, we have the left sided integral also. So here in this case we have alpha belonging to R also in this case, and here we can take a is equal to 0, and then if we take a is equal to 0 and b equal to infinity, then this will consider at the in the Riemann sense. Means in the Riemann he defined this integral. Riemann was the person who defined for a is equal to 0 and b is equal to plus infinity, and Liouville was the who defined this integral for a is equal to minus infinity to b is equal to infinity. So both way. So we can see that this fractional integral operator, they are satisfying this property. Okay, means semi-group property means they commute. They commute with each other, and this first property is called the semi-group property, and this property is called the commutative property. So if we have some power function, means x to the power n type things function, then the fractional integral of t to the power gamma is given by this function, and this is very much similar to the this Euler formula. Euler formula. Okay, so this is the natural generalization of positive integer property. Means if you have just n is equal alpha is equal to n, then we can differentiate this, and then we can find all these things. Okay, introduce the following causal function. Causal function means this for t less than 0, this vanish. Why this vanish? Why we need to define that this vanish? Because we want to define the fractional integral and derivative for t greater than 0. So this is for t less than 0, this will this function we define that this is plus sign, means this function vanish if t less than 0, and if t is equal to 0, then also we can say that it is 0. Okay, so here we can see that they are phi alpha t, and this convolution function. Convolution, this star denote the convolution of two function. So this is equal to phi alpha plus beta t, and similarly we can define our fractional integral in terms of the convolution of two function. One function is f, another function is phi alpha t. So j alpha ft is the convolution of two function phi alpha t and ft. Hence we know that we can find the Laplace transform of this fractional integral very easy, because we have the property for finding the Laplace convolution theorem. We have Laplace of the j alpha ft is equal to Laplace transform of phi alpha convolution ft. So this is L of phi alpha t and L of ft, and we just denote this Laplace transform of the function f by f tilde s. So in this way we can find that if we use the Laplace transform of phi alpha t and ft, we write f tilde s. We just this not denote, and what is the Laplace transform of phi alpha t is 1 upon s to the power alpha, and f tilde s is the Laplace transform of ft. So in this way we can see that Laplace transform of this j alpha ft is given by this equation. Okay. So now after defining this integral, what we need to define? We need to define the fractional integral, because our main motive is behind the how to define the fractional derivative. Okay, so we know that this dn means derivative of integer order, and jn means integral of integer order, and we know that they commute, and but this is not commute. So what we want? Actually, we want the fractional integral and fractional derivative. They should satisfy this property. whatever we define the fractional integral and fractional derivative, so we want that they should satisfy this similar property similar to the integer order derivative and integer order integral. Okay, so this property already we know that this is not true, because when we find the jn and dn, then what we know, what we get, we get some constant term. Okay, so similarly here this j and dn of ft is given by this formula. So now we are in a condition to define the fractional derivative of order alpha, and that derivative should satisfy this property: dn jn is equal to I, and jn dn is equal not equal to I means identity operator. So d alpha ft we defined as m minus alpha time the fractional integral of f, and then we take the mth derivative of the this integral, where alpha is lie between m minus 1 and m. Okay, so this in this way we are able to define the Riemann-Liouville fractional derivative of the function f. So here we know that if alpha is equal to m, then we have the integer order derivative. If alpha lie between m minus 1 and m, then we have this formula for the Riemann-Liouville fractional derivative. So here we can see. Hello, are you able to see my file slide? Hello.
Yes, sir. Visible, sir.
Okay, okay, thank you. So now what I was doing, I was defining this fractional derivative with the help of the Riemann-Liouville fractional integral. So here we can see that the zeroth order of the derivative and integral both identity operator, and d alpha j alpha will be identity. So it satisfies the first property of the integer order derivative and integer order integral, and similarly also it satisfies the second property. This property are satisfied by the fractional order derivative and integer both. Okay, so here d alpha of t gamma, this power function is defined by this formula. So this is well matched with the Euler formula, and here we have d alpha 1. So d alpha 1, when you apply this formula, we take gamma is equal to 0 in this formula. Okay, and then we will see that this Riemann-Liouville fractional derivative of 1 is not equal to 0. Hence, this is the one property which is not satisfied, which is not satisfied by the integer order derivative. So integer order derivative of constant function is 0, but here we have the fractional order derivative of constant function is non-zero. So due to this reason, this is we need some modification that which satisfy this property. Okay, also. So for this reason, this capital define the another fractional derivative. Okay, and then that fractional derivative satisfied the both the properties. Okay, here we have d alpha star ft is equal to, they just replace the fractional integral by the integer other derivative in this formula with respect to the Riemann-Liouville fractional derivative. So in this way we can see that d alpha star ft is equal to jm minus alpha df plus the mth derivative of ft. Okay, so we can see that this satisfies the property of this derivative and integer order derivative and integer order integral, and also you can see that if we just take in this formula, if you just take ft is equal to some constant number, then the integer derivative of constant number, this will be 0, and then the integral of 0 function of it will be either integer order or the fractional order, that will be 0. Therefore it satisfies the that fractional derivative of constant function will be 0. So it satisfies, now this capital derivative satisfies all the property of the integer order derivative. Okay, so this is the even better fractional derivative in comparison to the Riemann-Levy fractional derivative. So a definition. So here, but we need the one more thing. Okay, what we need here, that here we want to know we want to find the derivative of order alpha where alpha is less than m, but we need to know that what is the derivative of m, of the function f of order m. Okay, so we want to find the derivative of order alpha where alpha is less than m, but already we know the derivative of order m. So this is, in this way, this derivative, this capital derivative has the some disadvantage over the Riemann-Levy fractional derivative. Even fractional derivative does not need the mth derivative of the function, but here in the capital derivative we need this. So this is the restriction on the function, this definition. Even we need this absolute integrable of this function. Okay, so that is the one of the bad thing for the capital derivative instead of the Riemann-Levy derivative. Okay, so this is the relation between the capital derivative and the Riemann-Levy derivative. So the question is arise that is there any function for which the capital derivative of a function f equal to the Riemann-Levy derivative of the function f? So for in that case, we should know that this whole quantity here, this side d alpha ft will be d alpha star ft. D alpha star ft means capital derivative if this quantity, this summation quantity will be 0, and when this summation quantity will be 0, if this initial condition will be 0. So one positive thing is also with this capital derivatives, that in one positive things with this capital fractional derivative is also is that here we need the initial condition in terms of the derivatives, means lower order derivative of the function f. But in the Riemann-Levy derivative, we need the initial condition in terms of the integral and derivative. That will be the big issue. So that is also one bad thing for the Riemann-Levy differential operator. But here this is the good thing, but one bad thing for this thing, we need the more regularity of the function. Okay, so we have, I will show in the coming slide that there are under some condition this function will be equal. Okay, this means derivative of the Riemann derivative of a function equal to the capital derivative of the function. So here d alpha capital, this Riemann derivative of t to the power alpha minus 1 will be 0. If alpha greater than 0 means if the order of the power function will be less than the order of the derivative of the equation, then in that case we will have the equal to 0. Okay, so in this case we have j alpha d alpha t, this is 0, but here you can see that in one case you have j alpha d alpha t to the power alpha minus 1 equal to 0, and other case we have not equal to 0. So we can see that for this function, this j alpha d alpha and d alpha j alpha, they not commute. Okay, so j alpha d alpha not commute with d alpha j alpha. Okay, so this also satisfies this our property. Okay, this integer order similar property to the integer order derivative and integral. Okay, so here we have this that when these two things will be equal, the derivative of alpha derivative of f will be equal to the alpha derivative of g if f and g have this expression, and Also f and g have the same this expression if they have the capital derivatives. So Laplace transform, how we can find the Laplace transform? Laplace transform of the ft will be given by this formula. Okay, require the knowledge of bounded initial values of the fractional integral jm minus alpha. Why here we need the boundedness of the initial values? Okay, because we want to find this Laplace transform, and for finding the Laplace transform, we need this piecewise this exponentially bounded function. Okay, so due to that things also we need that this initial values of the fractional integral, they should be bounded for this d alpha ft. So this is the one bad thing with the Riemann-Lully fractional integral. But for this capital integral, we are even in the good better situation, because here we not have the integral. Here we have the derivative and integral, and then we need to know that they should be bounded. But here we have the only one initial condition, fk 0 plus. 0 plus means this 0 we taken from right side. Okay, so this thing is the only thing we need in the capital derivative case, and here we need, so this condition is little bad in comparison to the capital fractional derivative case. Here we know the exponent law for the integer order derivative and integral satisfied, but this exponent law is not satisfied for the derivative case when the m and n are the positive integer, this real number, and but this condition is satisfied. This condition is satisfied for the fractional integral. For the fractional integral, is this law of exponent is satisfied, but this formula is not satisfied for the this fractional integer fractional order derivative. So here we have that they are not satisfying. So for some function they will be satisfied, but for the some function they will not be satisfied. So in this way we can see that this commutative property is not satisfied, but this property is satisfied by the integer order derivative. So this is also one bad thing for the fractional order derivative. Okay, but integer fractional order integral, they are good as the integer order integral. So in this way we can we not have too much time. So here you can see also that d alpha, if we have that they are in the set of locally integrable. Locally integrable function means they are integrable not on the whole set, but they are integrable on the subset. So in that case also we can see that they are, so if they will be locally integrable, then we can find that our integral will this interval will be small. Then we can think that our function, maybe we can think in the loose sense that function may be bounded. So in this way we can find that this law of exponent is satisfied by this thing. Here we have this thing, and in that case we have this thing. So, and one application of this fractional integral and derivative is you can find in the Abel integral equation. This is the physics problem. So physics problem is the Tautog-Cron problem, and here we determine a curve in the vertical plane such that the time required for a particle to slide down the curve to its lowest point is independent of its initial placement on the curve. So this problem, mechanical problem of the physics, is represented by this integral equation, and this integral equation we can see that this is nothing but the fractional integral. We can replace this integral in terms of the fractional integral. So here u determinant is the particle position ut, the u tau represent the particle position, and ft will be the source, outside force applied on the this mechanical problem. Okay, so this is the Abel integral equation of the first kind, and this Abel integral equation is the one very famous Tautog-Cron problem, and this is the nothing but the fractional integral. Okay, so this is the, even before the 16th 17th century, it was this problem was solved by the Abel. Okay, so here how we can find this this Abel integral equation we can replace in this J alpha ut is equal to ft, and then we apply the d alpha on these things and we get ut is equal to d alpha ft, and then we can see that d alpha j alpha is equal to I, and in this way we can find the apply the Laplace transform, and then we can find that this is the solution of our Abel integral equation. Abel integral equation we can find by this thing. And now if we want to find the Abel integral solution of the Abel integral equation by using the Riemann-Liouville fractional integral or Kapto fractional integral, then we can replace this Laplace transform function in this form, and then in this form we can replace this by this Kapto derivative in the form of this Kapto derivative, and then we can find the solution of this Abel integral equation by using the theory of the Kapto fractional derivative. Okay, so this is the also the second kind of Abel integral equation. This thing also we can find the solution in the same way by applying this Laplace transform, and this way we can find, and then we can replace this resultant equation in the form of the two form. One form is we can replace by converting it in the this integral form, and another we can replace it in the form of the this derivative form, fractional derivative form, and then we find the inverse Laplace transform and we find the solution. Okay, so for the, in that case, for the Abel integral equation of second kind, we need to use the this function E alpha t lambda. This function is called the Mettag-Laplace function, and this is the Mettag-Laplace function is the generalization of the exponential function. Okay, so here this function is so Laplace transform of this Mettag-Laplace function is given by this equation. We replace that, we find this, and in this way we can take the inverse Laplace transform and we find the solution, and then we can use the fractional calculus theory to find the solution. So in the second way also, in the derivative form we can replace in the derivative form, and then we can find the solution. Okay, here is also the application in the heat equation. And what is the heat equation? Here we can find the solution of this equation in the form of this equation. Here this is the fundamental theorem of the heat, fundamental solution of the heat equation, and in this way we can apply this thing in terms of the fractional integral, and then we apply the fractional integral theory and find the solution. So if anyone have any question till now, then please you can ask. Anyone have any question? Okay, so here we have the same
Participants,
application.
you can.
Yeah, so these are the some references for the fundamental of this fractional calculus. So if you anyone want to
Good
ask
afternoon, sir. Good afternoon, sir.
yes, ma'am.
This is Dr. Rajbala Rathi from All India Chart Heroes Memorial College, Rohtak. So, how does this fractional integral help in solving the blood flow problem? Does it help there also?
Where?
Fluid problems.
Actually, ma'am, what happening nowadays? The people they just if because there are the fluid problem, there are the integer order derivative with that defined. So generally, people this is the bad thing for the people who are working on the fractional calculus. They just replace the integer order derivative by the fractional derivative, and they trying to find the solution. But that gives the little better solution, but still I think if you model with the fractional derivative, then maybe some change in the coefficient of the differential equation also. So, but they are not considering so. But there are exist such model in the literature. Okay.
Okay, sir. Thank you.
After this, we have I think 20 minutes. So for this, we have another thing, that is the little research level problem. So this is the controllability of fractional differential equation of order alpha lie between 1 to with non-instantaneous impulses. So what is the meaning of the controllability? Controllability means if we have some system and we want to find the achieve some target, that solution of the system satisfies some particular thing. Okay, so that particular things we known we say at the target point. So if we want that any system satisfy achieve the target from the initial point, the initial point and boundary condition, then this process is called the controllability. So achieving the target by using some suitable control parameter is called the controllability. And non-instantaneous impulses, I think people know there are the two kind of impulses. One is the instantaneous impulses, and another is the non-instantaneous impulses. So what is the instantaneous impulses means? In the daily life, if anything happens suddenly, okay, for example, earthquake for the very fraction of second, or when we we do the hammer on the some rod, then that is also happen the things for some fraction of second. So the when we do the hammer on the some rod, then dynamics is change of the rod. But what is the period and at which we apply the very extreme force is very negligible. So this kind of activities is known as the instantaneous impulses. Okay, and non-instantaneous impulses means if you have some activity which duration is not negligible, then we say that this kind of impulses is the non-instantaneous impulses. Example is, for example, if anyone have the sugar problem, so what happening that doctor give the insulin to the patient, then when a doctor inject the insulin in the patient, then it will take some time to act for the insulin for the patient. So in that case, this duration which is taken by to act by the medicine is called the non-instantaneous interval, and this phenomena is known as the non-instantaneous impulsive system. Okay, so these are the some application of the instantaneous impulses and non-instantaneous impulses. So here we want to study that what will be the controllability of the fractional derivative, fractional system, where if we take the order between 1 and 2. Okay, so controllability means we want to achieve the target. What is the control system? Control system means we have some system and the property of the some system is changing if we change some parameter in the system. Okay, so that parameter is called the control parameter, and whatever the target we want to achieve by taking this stable control is called the controllability process, and this controllability problem and this process achieving the target is called the controllability. So there are the different kind of controllability. One is the exact controllability, approximate controllability, null controllability. So exact controllability means we achieve the exactly same. We achieve the our target exactly. Okay, by applying the um, suitable control. Okay, and what is the approximate controllability? We not achieve the exact target, but we are in the neighborhood, small neighborhood of the target. We reach in the small neighborhood of the target. So this kind of controllability is called the approximate controllability. And then we have the null controllability. Null controllability means we start from some point. That point is known as the initial point, and then we reach to the origin. Okay, so this kind of controllability is called the null controllability. There are many more kind of controllability: trajectory controllability and total controllability. Trajectory controllability means we achieve the target along some path. This kind of controllability is called the trajectory controllability. Application of this controllability is in the defense too much. Okay, for example, if anyone want to fire any missile on some target, so if the missile target the exact location, then we say that it is the exact controllability. If it is not target the exact location and it is in the neighborhood of the location, then we say the approximate controllability. So this is the example of the controllability, and there are even in finance and mathematical modeling, many places there are the controllability. Okay, so here for example, this is the system one is called the control system, and here we have taken the finite dimensional control system. Here x is the our dependent variable and u is the control, a is the some matrix, and m is also matrix. B is called the control matrix, and x0 is called the this initial point. So this is finite dimensional, means x1, x2, xn. We have the system of equation, and then system of equation we have this things. Okay, so solution of this problem one, we know that is given by this equation number, this integral equation. And what is the meaning of this exact controllability? Okay, so here system one is exactly controllable in time t greater than 0 if for any given initial and final state x0, x1. Final state we called at the target. Respectively, there exists a control u, suitable control u, such that the solution of this problem one satisfy the target x at total time t is equal to x1. Means this capital T should also not be infinite, because if we achieve some target in infinite time, then there is no meaning. So we also need that we achieve our target in the finite time. So this set R is called the reachable set. Reachable set means reachable set is the set of all target point, and this for the suitable control U, and system one is will be exactly controllable if this target set is exactly the our whole space. Okay, means if you choose one initial point, then corresponding to one initial point we have the one target. Okay, so any target if we choose corresponding to x naught, then we can arrive from x naught to xt. Okay, so in this way we can say that our system is exactly controllable. If the rt is not equal, rn is not equal to r, then we will say that but closure r is equal to rn, then we say that our system is approximate controllability, means in the neighborhood. So there are the Kalman condition. He said that if this augmented matrix has the rank n is the number of dependent variable. So if this matrix, augmented matrix, has n rank, okay, then we will say that our system, this system one is controllable. So for finding the controllability of system one, we no need to find the solution of our this problem. We just need to know that what are the rank, what are the rank of this augmented matrix. If we this augmented rank of the augmented matrix is n, then we will say that our system is controllable. So this is the if and only if. Controllable, then rank will be n. If rank is n, then it will be controllable. So here we can take this matrix, and then we will find that in one case it will be controllable, and in the other case it will not be controllable. Okay, so here it is controllable, and in this case it is not controllable. So here are the some application in the this fractional calculus. Fractional calculus have the application in control theory, image processing, bioengineering, even for the finding the noise in the image. Okay, also people trying to now use the fractional model for finding the image processing. Okay, so here integral and derivative already I have defined, but here we have the same integral derivative, but here we need this beta between 1 and 2. In that case we have the m is equal to 2 here, m is equal to 2, and then same formula that will work for the fractional integral and derivative of order 2. Okay, so here, because this is the second order alpha lie between 1 and 2, then this kind of system is very much similar to the second order wave equation. Second order wave equation, and we know that if we have the wave equation, then we need to use the sine cosine family for finding the solution of such system. So here for the finding the solution of equation number 5, where alpha is the between 1 and 2, for this thing we have this definition of the cosine family, alpha order cosine family, and this is the satisfy these three conditions. Okay, so if C alpha t satisfy these three conditions, then we say that C alpha t is the cosine family is strongly continuous alpha order fractional cosine family. This is the solution operator. Okay. Similarly, for this related to the cosine family, we have the sine family. Okay. Related to that, this S alpha t we have in this form, and then this is the relation between C alpha, and then we have the Riemann-Liouville family. Associate fractional is associated with C alpha is defined by this thing. Okay, P alpha t, and this is the our research problem. This is the research problem. This here we have the finite dimensional system, and this is the forcing term, and A and B are the matrices, and here Ji and Ji2 they are the impulsive function, and these impulsive function they are not the non-instantaneous. They are not instantaneous impulses. They are non-instantaneous because here the instantaneous this impulsive condition is satisfied is defined on the interval. This interval is defined on the this impulsive condition and this interval. Okay, so in this way we can have that this and these are the initial condition. So we can find the solution of this problem 6 by applying the fractional cosine family and related to sine family in the form of the, you know that these are the impulses. These are impulses, so they are the discontinuity. Therefore, we need the solution space must be the piecewise space, piecewise continuous space. Solution space here it will be the piecewise solution PC space, space of piecewise continuous function, and this piecewise continuous function with this norm will be the Banach space. And now we will use the Banach fixed point theorem for finding the controllability and all these things. So instantaneous impulses, we have the duration is very small, and non-instantaneous impulses, there the duration is not negligible related to the whole time process. Okay, so solution of our problem, fractional problem, will be given by this equation number 7. Okay, and this is called the mild solution. Mild solution means this is the solution of the integral equation corresponding to the derivative. This is not the solution of the real differential equation. This is the solution of the integral equation. So solution of the integral is called the mild solution, and if we find the solution of the derivative differential equation, then it is called the classical solution. So mild solution is very much similar to the weak solution in the partial derivative, partial differential equation case. Okay, so if we have partial differential equation, and then the weak solution in that case is very much similar to the mild solution in this case. Okay, so here we need the to show the existence of solution and controllability, we need this Lipschitz condition on the function f and boundness and b and all other things. Also we need this WSI plus 1. This is called the this is the one operator. This is called the control operator, and also the it has some special name, and this operator should be invertible. If this operator will not be invertible, then we cannot find the controllability of our system. So these under this condition, we are able to prove that our system is has the exactly controllable on this our interval this thing, and if this condition is satisfied, and this condition we can say that it's satisfied because here this is the capital T, it is in our hand, so we can take capital T in such a way that this whole thing is less than 1. So outline of the proof I am not going to give. We use the Banach fixed point theorem for finding the. So we define the one domain of the function f, and then we will prove that this function has the fixed point in the domain. Therefore, it has the solution. Okay. So remark also we can find this we can use the interpolation property to find the missing at the missing point also the solution. But here due to that time, we can even extend this result to the integral differential equation. Means if you have the integral term in the our original problem, then also we can find the solution. So here we have this problem application example. So this is the very complicated damped problem. Okay, damped fractional order partial derivative. Okay, so what we did, we converted this partial derivative in the form of the ODE in the L2 space, and this conversion of the PDE into the ODE in the L2 space is called the abstract formulation. Okay, so here this second order derivative we denote by this operator A. Okay, and this operator A we define by using this ax is equal to minus n square x xn xn. This property we use the applied function analysis to find the solution. Okay, and then this is the expression for this cosine operator, and here by this all setting we can say that our PD can be written in this OD form. So conversion of the PD in this OD form is called the abstract formulation. And this why we do the conversion of PD in the abstract form, because when you solve the PD, then for each PD you need the different calculation. But if you have the abstract differential equation, then this f will be the one class Lipschitz, for the any Lipschitz function. This problem has the solution which satisfy the Lipschitz condition for the function f. If function f satisfy the Lipschitz condition, then this for this class of the function, we know that there are not only one Lipschitz function. There are the many Lipschitz function which are satisfying the Lipschitz condition. So this result of the problem, this is not true for the one problem, it will be true for the class of problem. Okay, therefore in this way also this method is good, important. So this method is called the, you can say, the cosine family method. Even if you have the integer order derivative, okay, integer order derivative, then you have this semi-group theory of linear operator method to find this different solution of the differential equation in the L2 spaces. Okay, so here we have the big expression, need the very deep knowledge of the functional analysis. Okay, so in this way we converted this, and here we have another example, this damp example, and then Ct is given by this cos functions, St given by this sine function, and A is given by this function minus a1 is the constant. And here this is the damp second order, you can see that this is the second order damping problem, okay, with impulsive condition, non-instantaneous impulsive condition. So this problem, solution of this problem also we can find by using the same method what I have done here. Okay, so in this way these are the some important references for this second order controllability problem. So this is the fifth and third, this is the important for the finding the cosine family and sine family theory, related theory. Okay, and this result you can find in this my paper, in these two paper. In three paper you can see that you can find this thing. So here trajectory controllability means we achieve the target along the some trajectory. Okay, so thank you. Any
Thank you
question?
so much, sir, for your detailed and insightful session. We'll now like to open up for discussion. Anybody who would like to ask anything can unmute themselves, or otherwise they can also leave it in the chat box. We'll read it out for you. Any participant?
I think either they not understand anything or they understand everything. Okay.
We'll decide with the former, sir.
Yeah. Yeah. Okay. So
As I do not see any queries coming in, I'd like to proceed
yeah,
and
if there
take
is
this
a question,
opportunity to
then I
propose
like
the
to
vote of
thanks again
thanks.
to all the participant and organizer for this invitation. Thank you.
Allow me an opportunity to propose the vote of thanks, sir.
Yeah, sure. Please.
On behalf of the organizing team and all participants, I extend my sincere gratitude to Professor Muslim Malik sir for giving his valuable time and enriching us with his practical knowledge today. Your talk has truly added immense value to our today's program and also our FDP program in general, and we look forward to many more such interactions in the future. Thank you once again, sir.
Thank you, ma'am.
Thank you,
Thank
sir.
you. Okay, bye.
Delving further into the event, we have our second resource person with us, Dr. Abhishek Kumar Singh. Sir, have you joined?
Yeah, I'm here. Am I audible?
Yes, sir, you are audible.
Yeah, thanks.
Sir, your video is off.
Yeah, just putting on. So my slide is visible.
Yeah, your presentation is visible to us.
Yeah.
Sir, allow me a moment. I'd like to introduce you to our participants.
Sure.
Our second resource person for the day is Professor Dr. Abhishek Kumar Singh, sir, Professor of Mathematics, Department of Mathematics and Computing, IIT ISM, Dhanbad, Jharkhand. Dr. Singh has completed his MPhil and PhD in mathematics from IIT Dhanbad. With more than 15 years of teaching and research experience, he has published over 200 research articles. Topic of his today's talk will be differential equations as a tool for seismological modeling. Now, I would like to invite Professor Abhishek Kumar Singh, sir, to kindly deliver his lecture. Thank you so much, sir, for accepting our invitation.
Thank you. First of all, before I actually start, let me thank to the organizing team, especially Dr. Prerna Sharma and Dr. Ajit Kumar Singh for having me here for this FDP program. My sincere thanks to Sardar Vallabhbhai Patel University of Agriculture and Technology, UP. So without wasting time, let me start my presentation. So I think I'm perfectly audible.
Yes, sir, you are audible as well as your presentation is visible to us.
Fine, fine. So yeah. So today I'm going to talk on differential equation, which is to be used as a tool for seismological modeling. So in my talk today, I'll be basically going through some of the basic part, especially some of the basic prerequisite in a very brief way, and then finally I'll take up a very simple problems of to understand how the propagation modeling of Love and Rayleigh wave basically is accomplished by means of a differential equation. And this was basically in the beginning of 20th century that these particular modeling has basically prevailed in the literature, and finally there's a lot of advanced work has been done by different researchers, not only in abroad but also there are very good groups in different part of the country for this theoretical seismology. So so this is the outline, and first I'll be talking in very brief about introduction, and then taking up the Love wave propagation modeling, and then Rayleigh wave propagation modeling. So the things will start with the understanding of elasticity. Generally, we encounter this type of term, especially in our class 10th, or you can say 11th. So elasticity basically in solid, in a very you can say for the understanding of a layman, it can be said as elasticity in solid refers to the ability of a solid material to return to its original shape and size after being deformed by an external. Means once we are removing the force, it should come to the original shape and size. And this property is very crucial for material to withstand the forces and return to the original form. So the seismological modeling which we basically take up will be considering the seismic wave as an elastic wave and the medium of the earth as elastic medium. Consideration of this particular means this particular assumption is seems to be not realistic, but basically it defines most of the phenomena of seismological studies. So this is the one of the basic term about the elasticity and what it basically means. So this is what basically we understand as a beginner. Now the we have to understand what is basically the just what is the stress. So in solid mechanics, stress is defined as an internal force. When we are putting some sort of force, definitely some reactive force which is developed inside the material. So that's why it says that in solid mechanics, stress is defined as the internal force acting in a material per unit area. So when it arises when external force are applied to a solid, causing the material internal particle to resist deformation, because every material in the normal state wants to be stable. So if basically we deviate it from the stability, definitely it'll try to regain its original positions. So therefore, to regain its original position, some internal force is being developed, and that is basically a measure of those forces per unit area is basically the stresses. So these stresses may be classified. Basically, there are different ways to classify, but the thing is, majorly it is classified in two parts. One is called normal stress, when we talk about the stress perpendicular to the surface area, so that is a normal stress. And when the force which is causing the stress is basically tangential to the material surface, so that
Dear, dear participants, our resource person is facing technical glitches. Let us join. Provide us a minute or two.
Yeah, hello. Hello, am I audible?
Dr. Abhishek, can you hear us?
Yeah. Yes, yes, yes.
All right.
I think there was some technical issue, and now, should I start now?
Yes,
Because
sir,
the
you can
slide
go
is
ahead.
visible, and I think I'm also
Your fifth slide is visible to us. Now
Right,
the
right.
fourth one.
fine. So, I was talking about the stresses. I think everybody has just attended this particular part, or should I start from the beginning?
I think, sir, we were able to follow you till here.
Okay, fine. So I was talking about there are two types of stresses. One is normal and another is shear. And associated with these stresses, there are two types of strain. One is normal and another is shear. So now moving ahead, I'll be talking about the classification of the seismic wave. And later on, we will take up two particular surface waves and we'll discuss on its mathematical modeling. So basically, one important thing is we call earthquakes as a seismic disaster. It is hazardous because of the shock wave generated at the focus of the earthquake. Focus of the earthquake basically lies inside the earth, but the epicenter is just at the surface of the earth, which is at a minimum distance from the focus, which is inside the earth. And it is the most affected part of the earth's surface, which is called epicenter. So these shock waves, when which are generated due to the earthquake, are called seismic waves. And these seismic waves, once generated, they travel in all directions with their characteristic velocities. And they are recorded on seismographs. So if we talk about the classification of the seismic waves, basically they are of two types. One is called body waves, another is called surface waves. Now, body wave is basically divided into two further parts. One is called P wave, that is primary waves, and another is called S wave, which is secondary wave. And there are several types of surface waves, but two, the most important one are love waves and the Rayleigh waves. So these are the broad classification of the seismic waves: body wave, surface wave, body wave as P wave and S wave, and surface wave as love wave and Rayleigh wave. Just we will try to have a look on these waves and how they basically travel and how they are recorded in the seismograph by means of some animation. So this is the animation of 2004 Sumatra earthquake. It's also called as the Indian Ocean earthquake. The intensity of this earthquake was measured around 9.1 on the Richter scale, and a lot of calamities happened on the eastern coast of India, especially on the Marina Beach. That's one disastrous earthquake happened, and it basically led to the tsunamis. Now, this is another animation which tells how that these seismic wave propagates. So you can see here that it basically gets generated inside, and once it traps on the crustal upper part of the earth, a surface wave generates, which is basically having a very high amplitude. So let us have a look again. So it's generated, body waves and are coming, but later on, surface waves are being generated, which are basically the most disastrous one. So what we have seen that the body waves are basically of two types, P wave and S wave. So here we are going to discuss in very brief about the fundamentals, what the P wave means. It's basically primary wave. Primary wave, it's a longitudinal in nature. Longitudinal means the particle is basically moving back and forth. Means the direction of the wave is towards the x-axis. If you can see that our x-axis is the direction of wave propagation, and the particle is also moving back and forth. So it's a longitudinal in nature, and because of this, it is having the highest velocity. So P means primary, and why it's primary? Because it is the first one to be recorded on the seismograph. And the velocity of this P wave basically depends on the medium in which it is propagating. It's around 1 to 14 kilometers per second when it's generated. Now here comes the second body wave, that is called S wave, or it is also called secondary wave. Why it is called secondary? Secondary because it is being recorded on the seismograph after P wave. Now, the nature of the wave propagation of S wave is basically transversal in nature. Wave is propagating in X direction, but you can see that particle is moving up and down. So it's perpendicular to the direction of wave propagation. So the wave is basically transversal in nature. It may be up and down, or it may be side by side, but it is to be perpendicular to the direction of wave propagation. Particle motion should be perpendicular to the wave propagation direction. Now afterwards, we will talk about the two very important surface waves which we have discussed, that is love wave and Rayleigh wave. So first let's start with the love wave. Love wave is basically a kind of surface seismic waves. Basically, when this surface wave basically occurs, when actually during the you can say occurrence of the earthquake at the focus, these primary and secondary wave generates, these are body waves, and when they basically comes toward the crustal part of the earth, means that's the upper part of the earth, they basically get trapped, and there are a lot of superposition happens on it, and finally this type of surface basically gets generated. One is love wave. This velocity of love wave is basically, you can say, it's nearly 2 to 6 kilometers per second. And the secondary one, the fastest one is primary wave, it's 1 to 14 kilometers per second. Then secondary wave is 1 to 8 kilometers per second, and this is nearly 2 to 6 kilometers per second. So that all depends on the medium, but this is a you can say that's a rough range of the propagation of these waves. Now, if you can see that that this is a surface wave. Why is surface wave? Because its most impact lies on the surface. As you go downwards, you can see that the amplitude dies out. So on the upper part of the you can say on the top surface, near the top surface, the amplitude is quite high. But if you go downwards on towards the z-axis, the amplitude basically goes it basically dies out. You can say it decays. So here also love wave is a transversal in nature because you can see that particle is moving side by side and the wave is propagating in X direction. So it's a transversal wave. But the thing is, it's quite different because it is kept in the category of a surface wave. Why? The reason is here the wave propagation, the amplitude dies out with the depth. So that's why its impact mostly is on the surface and where we basically reside, and that's why these are the disastrous waves. The second one, the most disastrous wave, disastrous seismic wave, is the Rayleigh wave among all. Why? What's the reason? The reason is you can see it's a propagation pattern. Here, it is having both the feature. It is longitudinal in nature and transversal. Why? You can see that when wave is propagating towards X direction in the Rayleigh wave, you can see that particle is following an elliptical path. It's an elliptical path. Means, and where this elliptical path is basically traced out, it's an exit plane. An exit plane means ellipse is formed, and you can say in an exit plane. So when ellipse is going to be formed in exit plane, some component is working towards X and another component working towards Z. And when the component which is basically working towards Z is basically giving rise to a longitudinal characteristic, and another which is propagating towards Z is giving rise to a transversal characteristic. And that is why the Rayleigh wave is both, you can say it's dilatational and distortional, having both longitudinal and transversal characteristics. And that's why this Rayleigh wave makes a solid medium flow, you can say move like a ocean waves. It makes the you can say solid part of the earth moving like a oceanic waves. So it's very disastrous, and the speed is 5 kilo, you can say 50 meter per second to 4 kilometer per second. But the thing is, it is you can say it's most disastrous. So here we are going to take up the modeling of love wave and Rayleigh wave in today's presentation, and in a very simple medium to start with, and that is called isotropic medium. So before I actually take up the medium, let us have a look how these waves are being recorded on the seismograph. So on the top picture, you can see that there is a seismograph. It's recording the different vibrations. It always records some of the vibration, because if earthquake is not occurring, even then there will be some vibration. But when the earthquake occurs, you can see that different waves are recorded. You can see this part is a noise, which basically occurs every time. But whenever there is an occurrence of earthquake, there is earthquake, or you can say a major explosion occurred somewhere, definitely at some seismic station it is going to be recorded. So this is the arrival of P wave, then arrival of S wave, and then arrival of surface wave in the last. So the first one is P wave, then second one is S wave, and third one is the surface wave. And you can see the amplitude also. The amplitude of surface wave is also very high. So that is why these are very, very dangerous waves. So we are going to take up two waves for our mathematical model. One is called love wave, and then another one is Ara wave. So let's start with the love. Actually, the love wave is being named after a British mathematician named H. Love. And the modeling is being done in 1911. Now let's talk about how that particular love wave propagation is being modeled. So here we are considering a simple structure. There is one layer of width h. Width of the layer is fixed, but length and breadth is infinite. And there is another, that is semi-infinite medium at the below the layer, and that is semi-infinite medium means layer and you can say layer and breadth are infinite, but here the width is also infinite. It is having one boundary which is there because of the layer being started, and another part is basically extending towards the infinity. So the below one is called as a semi-infinite medium, or it is also called as a half space, and upper one is a layer because it's having a, you can say it's a finite. In such a structure, the material is assumed to be isotropic homogeneous. So let me give a very small idea about the isotropic and homogeneous. Isotropic basically means that such a material in which your material properties are same in all possible direction of a point. So that is being called isotropic. And the isotropic medium is the simplest one, and you can say the two stiffness constant are associated with these materials, and that is called Lamè's constant, lambda and mu. Mu is shear modulus, and lambda basically is accounting for the volumetric, you can say, strains and volumetric shear modulus. And homogeneous means those material properties is not going to be a function of any space variable. If it is going to be a function of a space variable, it is called heterogeneous, inhomogeneous, or functionally graded. And if and isotropic or anisotropic, there are two types of you can say the material mediums. And isotropic is the simplest one. And as you increase the anisotropy to the large extent, you can have a more complicated constitutive equation to deal with. So here I'm going to take up a very simple material medium that is isotropic in nature, means all the material property are same in all possible direction with respect to a point. And those material properties are also going to be a constant, not a function of space. So because of this, now let's move ahead to model the problem. We know we have to introduce some coordinate frame of reference to start our modeling, so as to connect it with some, you can say, with the coordinate geometry, and further with the differential equations. So we have to assume something. So let that the density and the rigidity is mu1 and ρ1 for the layer, and mu2 and ρ2 for the semi-infinite medium. Then the thickness of the layer is assumed as h. We need to keep in mind that its breadth and, you can say, the length both are infinite. The coordinate system is considered in such a way that the direction of wave propagation is along the x-axis, and the z-axis is vertically downwards. And u, v, w are the displacement component along the x, y, and z axis. Now, since we are dealing with the love wave propagation, And we need to understand that, yes, for the love wave propagation, there is a specific pattern we have seen in the animation that the displacement, it's basically the love wave is transversal in nature. The second thing is, what are the displacement components which are there? We have seen that particle is moving side by side. There is no motion vertically, means towards the, you can say, towards the x direction and towards the z direction. It's moving only towards the y direction. So that's why V component. But this V component means the side by side motion amplitude, which is giving rise to the amplitude, basically dies out with the depth. So that's why it's going to be a function of z. Of course, with the function of, it's a function of time. And since the wave is basically progressive in nature, so it's going to be a function of x as well. This love wave is called anti-plane wave because it's basically perpendicular. The motion is perpendicular to the XZ plane. We have seen the XZ plane. It's perpendicular to the XZ plane. It's called anti-plane wave. With this particular notion, keeping in mind that the wave propagation, for the love wave propagation, the particle characteristic for the vibration is basically given by 1. Now, the body force. We know that when we have to talk about some sort of modeling, we need to put up some field equations. And definitely the conservation laws basically comes into picture. The conservation laws, basically here we are dealing with a simpler case, and it's basically law of conservation of momentum taking up. So it's basically giving rise to 2. So it's written in the tensor notation, tau ij is a stress, and comma j means the differentiation, partial differentiation with respect to j. J means j is varying from 1 to 3, means corresponding to x partial derivative, then y, then z, like this. And ui means it's ui is varying 1 to 3. So u1 is u, u2 is v, and u3 is w. So in the component form, if you go write the same equation 2 in the component form, although it's written in the tensor form, it will give rise to equation number 3, equation number 4, and equation number 5. These are 3 equations. Now, since we are dealing with love wave propagation, the medium is isotropic and homogeneous. So we need to have some constitutive equation. What is constitutive equation? It's something which relates the stress with the strain. And here is the constitutive equation for isotropic type of wave. If you see simply here, it's 2 stiffness constant lambda and mu are appearing. This is Kronecker delta. You know that what is Kronecker delta? Delta ij, when I equals to raise 1, otherwise it's 0. Lambda is basically one stiffness constant associated with the volumetric strain. And volumetric strain means, you know, that if volume gets changed, so definitely, so that term is being given by the delta, cubical dilatation, volumetric strain. So that's why lambda is associated with this one. And mu is a shear modulus. So there are 2 stiffness constant, lambda and mu, for the isotropic medium. Apart from that, there is a delta term which is called cubical dilation. It is accounting for the volumetric strain, means change in the volume upon original volume due to the occurrence of these particular waves. Mu is a shear modulus. And this epsilon ij is nothing but these are the strains. So stress is related with the strain, accounting for different type of constants. That's lambda and mu. So now we proceed further, and we'll try to figure out what are the epsilon ij's, because tau ij is depending on epsilon ij, and epsilon ij should be depending on the displacement. So epsilon ij equal to ui comma j plus uj comma I means displacement components are being partial. You can say it's a partial derivative of some displacement. So it's an average one, and finally the divided by 2. So if we finally figure it out, depending on the nature of love wave, which is given in 1, if we finally able to calculate these epsilon ij, because it's depending on the displacement, and finally putting up in this equation to find out the stresses, and then putting up in equation number 5, 4, and 3, we will be able to get the governing equations. our main task is to frame out those governing equations, and for which what we have to do, we have with us stress strain relation, constitutive equations. We have the strain displacement relation, and let us find it out this the different strains in terms of displacement. We know that in this case u and w are 0 and v is only non-zero, which is depending on x, z and t. So we have calculated epsilon xx, which is normal strain in x direction, which is coming out as 0. Normal strain in y direction, again 0. While normal strain in z direction again 0. Now this particular thing is telling one very important part, that cubical dilatation in this case, volumetric strain, is going to be 0 in this case. So therefore lambda terms is not going to appear in the problem of this Love waves. Now there are different, you can say these are shear strains, xy, xz, yz. If you calculate based on the condition of wave propagation, of Love wave propagation, you'll be able to get that epsilon xy is something depending on v with respect to x, and then epsilon yz depending on v partial derivative with respect to x. Now substituting, we'll be able to calculate those stresses. We find that not all stresses are 0. There are some which are non-zero. And if we substitute in those component form equations, then finally we'll be able to get equation number 20, which is finally written in the form of 20. So finally we have got a linear partial differential equation. It's looking a very simple equation, not very complicated, because the medium which we have selected is simple. Aluminum epoxy is one of its example of isotropic medium. There are different anisotropic medium which basically give rise to complexity, and different type of equations basically encounter in place of tangible. Now, here beta is basically the shear wave speed under root mu upon rho. We know that we are having two medium, one layer medium and one semi-infinite medium for our study. So considering that u1, v1, w1 is for the upper medium displacement due to the occurrence of those Love waves, and u2, v2, w2 is for the half space, or you can say semi-infinite medium. Now the equation 21 with the subscript 1 for the upper medium and 2 for the lower medium can be written as 22 and 23. Now beta will be for beta 1 for the upper medium and beta 2 for lower medium. So this is the equation. So we are right now, we have made ourselves equipped with the equation 22 and 23 for the layer medium and for the half space or semi-infinite medium for the propagation of Love tank. Now we need to solve these. To solve these, we need some boundary condition as well. So what is that? Since this is a shear wave, is an anti-plane shear wave, and the surface, as per the geometry, we have drawn that there is a xz plane. Finally, the upper surface is stress-free. We are not assuming any extra stresses which is there on the top surface. So this is what in giving rise to a equation. So it's a traction condition. We know that on any surface there are three stresses associated with that. One is normal and two are shear stresses. And what is that surface? Surface is z equals to minus h. It's z equals to minus h means it's a plane perpendicular to the xy plane. So for that particular plane, the traction which are non-zero, which are going to contribute for the stresses, is nothing but tau yz only. Because that particular surface which is parallel to xy plane will have a normal of, in the direction, you can say normal as k cap. So because of that, only this particular shear stress come into picture to contribute towards the boundary condition. Although mathematically one can derive this thing, but the thing is, it's basically the stresses, shear stress. And at the common interface of the layer and semi-infinite medium, we have a continuity of displacement and continuity of the stresses. Now with these are three boundary conditions, two at the common interface and one at the top interface. There's the simple one being taken. Continuity of displacement and continuity of stress is a very ideal case. Basically, it happens in when both the mediums are in very nearly, you can say, are very similar in the elastic properties. You can say very similar type of medium, but still, it's a very welded case, and it's very ideal case. It doesn't happen always in most of the time in the practical scenario. So the many people used to consider the imperfections. Since we are dealing in a very small, very, you can say, this is the starting of the seismological modeling. So we have taken a very simple case, the ideal case, that is what continuity of the stresses and continuity of displacement at the common interface, which is given by 2526, and upper surface is stress free. So these conditions can be tweaked around with the different theory, which is defining the practical scenario in more closer way to give rise to the different complexity, and which are basically such type of problem is being solved nowadays. So taking up these boundary conditions and these equations 22, 23, now we have to find the solution. Now, to find the solution, we have to assume the solution like this. What made us to assume the solution like this? The reason is this love wave is having a characteristic of sinusoidal in nature. You know that sinusoidal functions that is having an oscillatory function like cosine sine curves. So love wave is also having such type of profile. So because of that, e for I kx minus ct is basically appearing. This particular love wave is progressive in nature. It's not a stationary wave. It's a progressive wave. It's harmonic in nature. It's sinusoidal in nature. And because of that, e for I kx minus ct term is occurring for the solution of such particular governing equations. The one thing is very important, that this V1z is there, which is associated with the amplitude. As we have already seen that the love wave is such kind of wave in which basically the amplitude basically is depending on z, and as z increases, it decays, it dies out. So because of that, the 21, 27, and 28 basically give rise to such, means we are assuming the solution like this. This assumption is completely justified as per the nature, as per the characteristic of love type wave propagation. Now, if we assume the solution like this, we have the main thing, we have to find that V1 and V2. If we substitute this, where K is what? Wave number. Wave number is associated with the frequency, and C is what? Velocity of this love wave. Phase velocity of the love wave. Now, if we put this solution 27 and 28 in the equation, we are going to get 29, and for the half space, and this is going to be 29. And this is a simple ODE, and if you solve here, you are going to get this type of solution for V1. V1 is what? Amplitude depending on Z, where A and B are the arbitrary constant. And if we substitute this, and similarly, we have assumed the solution for the half space as given in 28. Now, if we substitute it in equation number, we can say this 23rd, we'll get a ODE again, and this is going to be 31. This, and finally, we can get the solution. But we have to take, if we solve it, we'll get a solution in the exponential form. But the thing is, we have to put it in the consistent form. What is that consistent form? It is basically the propagation dies out with the depth. So there should be a negative exponential function, basically obeying the nature will basically good for the modeling, not the positive exponential function. So because of that, we are going to get the solution Huntington. Now, we got that solution for the semi-infinite medium, V2, the amplitude, and V1. So because we got V1 and V2, capital V1, capital V2, we can compute the displacement, but with the arbitrary constant. We have how many arbitrary constant? 3. And we are having how many boundary conditions? 3. So if we substitute in the boundary condition, we will get these 3 equations. Now what we want? We have to solve this equation. This is the homogeneous linear equations. And now for having a non-trivial solution, definitely we'll get right. For that condition, we are going to get this equation. And this equation is nothing but a dispersion relation, or you call it as a velocity equation. And what is dispersion relation? We can rewrite, we can expand this S1 and S2 in the form, and we will get this particular equation. S1 and S2 is already there in the defined earlier. So just we are substituting the values. So 37. So this is the classical love wave equation. This is the velocity equation. What we see that the velocity of the wave is depending on K. And K is wave number. And it is related with the frequency. Means different frequency component of the love wave travels with a different speed. And that is what the characteristic of love wave is. And that's why this love wave is dispersive in nature. Is basically dispersive in nature. Now, it's not always possible that love wave propagates. This is the classical love wave equation. If you see, for this square root to be positive, for this square root to be positive, there should be some condition. This should be less than 1. For this to be less than 1 and for this to be greater than 1, we finally get a validity condition. Means your C, which is the velocity of love wave, is basically valid when you have such a layer which have the associated bulk shear wave lesser than its, means the velocity of the bulk shear wave of the layer should be less than the velocity of the bulk shear wave of the half space. If such a configuration is there, then one can study love wave. Otherwise, it's not going to be allowed. This is a wet validity condition which basically happens, and finally this validity condition is being mathematically proved by this model. So this is the simple one, and let us, if we simply go for the plotting of this particular equation, dispersion equation of love wave, we need to have some data. And from the little book on planet Earth by Gobbins, if we take the data for the Earth crust as this and this, mu1 and rho1, mu2 and rho2, we'll finally get a curve like this. It's a dispersion curve for this particular data. And you can see that for different kh, it's a dimensionless, it's made as a dimensionless. K corresponds to frequency. For different k's, you are going to get different c by beta. Again, it's made dimensionless. So for different k, you are getting different c. Beta 1 is fixed and h you can think of. So for different frequency, you are going to have different wave velocity, and that is what is being told by that relation. So this dispersion relation is very important tool for seismologists. If one can trace the dispersion relation, they can predict about, they can predict many information from this dispersion curve. If dispersion curves basically you can say that this velocity basically gets lesser or higher with respect to some parameter, it tells a lot of information about the density, about the stiffness, about the different, you can say, about the different configuration of the medium. So that's why you know that without digging a lot in the earth, the scientists, the seismologists are able to predict what, up to how much, which type of a structure is. I mean, where is the, up to what depth there is crust, what is it is made up of, fine, and then there is a mantle, then there's a core. Have anyone digged on? No. But still, just by getting those waves penetrated inside and getting its reflection back and studying those reflection patterns, one is able to understand what is there inside Earth. So that is why this is called a non-destructive testing, and that is what is being used in civil engineering, for mechanical engineering. You know that bridges, the health monitoring of bridges or building is also being done. Without damaging anything, one can predict that whether there is some crack developed in the foundation of the building or in the pillar of the bridges or not. So such type of for such type of detection, for such type of non-destructive testings, these waves are very important. This P wave, S wave, or sometimes the sensors are very important. So I've talked about this application of these love waves in very brief, but one aspect of these love wave that when we don't want it to be generated, especially during the earthquake, it is going to be a disastrous one. It completely abolish the structures and all. But if we generate it as per our intentions, our requirement, it can be a value. You can say it can just give us a lot of application in different sense. So there are many love wave sensors and all. So just to gather a lot of information, because wave is having a very beautiful property that it contains the information. It's basically come up with the information of the medium through which it is basically coming off, or it has traveled through. So this is a very important part, and that is love wave. And let us move to the next part of today's lecture, and that is Rayleigh wave. We have seen that it's the most disastrous one. Although the speed of this Rayleigh wave is slow, but because of its dilatational and distortional nature, it's a most dangerous one. So today in the model we will try to see that what is going to be its velocity. Whether we have seen that the fastest one is P wave, the second fastest is S wave, and in fact Rayleigh wave, the velocity is lesser than both, and why it is lesser than both. So we will try to see by means of this modeling. So Rayleigh wave, here just we are considering a simple semi-infinite medium. I have already just explained what is semi-infinite medium, that is having one boundary one side and no boundary on the other side. It's a half space again. You can see that this top surface is there, but on bottom it's not. It's look like it's a cuboid, but it's not a cuboid. It's extending towards z-axis, right? And there is its length and the breadth both are infinite. Again, the medium, semi-infinite medium which we have considered, is isotropic in nature and homogeneous. Isotropic, again, the medium, that particular medium is having all the properties, all material properties same in all possible direction about a point, and those material properties are not depending on the space variables. So just owing to that, we know that we have already seen that for the isotropic medium, what is that? Stress-strain relation, that constitutive relation. And we have also seen what is the strain displacement relation. One thing is to be understood that we are considering the earth medium as elastic one, and we are considering that the strain is happening in a linear fashion. It's not non-linear. If one has to consider non-linearity, then that epsilon ij, which is ui comma j plus uj comma I divided by 2, will have some other component as well. Some other terms will be there. Non-linear terms will give rise to non-linear differential equations. But as I already told, that most of the phenomena of seismology, seismological studies are being, you can say, defined by this properly. So it's no harm to consider it as a elastic medium. Now, again, for the modeling, we are considering that this particular medium is having the stiffness constant lambda mu, which is Lamè's constant, and density rho. The coordinate axis is again considered in a similar fashion, that x is the direction of wave propagation, z is vertically downward. And this medium is extending towards z. This is not, it doesn't have any bottom limit. It extending towards z. And u, v, w are the displacement components along x, y, and z axis respectively. In the Rayleigh wave propagation, the particle motion is something different as compared to love wave. We already seen in the animation. What is that displacement pattern is? U function of x, y, and t, w function of x, y, t. It means there are, since it is both dilatational and distortional, the propagation will happen something in an elliptical fashion. It will go like this. So elliptical means it is proceeding further towards the direction of wave propagation. So it is longitudinal in nature. And since it is just moving up and down as well, so it's having a transversal component as well. So that's why U component and W component will be there, but there will be no V component. And that is what reflected here in equation number 38. U and W components are there, V is not there. And del Y is not equal to 0. This is basically a plane wave, and del Y is not equal to 0. It simply means whatever is happening in this XZ plane, the similar thing is happening in all other plane parallel to this. That this del Y identically to 0 means the parameters is not depending on Y. The quantities are not depending on Y. It physically means that whatever the phenomena is occurring in this XZ plane, the same thing is occurring in other plane parallel to this XZ plane. And that is why we are able to convert this three-dimensional problem into two-dimensional. And that is what that also happened in the case of love wave. It's very important. Now, because of this particular propagation pattern, we should have some sort of stresses. Because of this particular propagation condition, we will have different strains, normal and shear strains, as like in love wave, but most of the strains were 0 in that case. But here in case of Rayleigh wave, it's not like that, because two components are non-vanishing. And because of those strains, there will be several more stresses which are non-zero. In love wave problem, most of the strains, most of the stresses are 0. But here in the case of Rayleigh wave problem, we have most of the strains and more of the stresses as non-zero. Now, if you simply substitute in the conservative field equations, and those field equation will finally give rise to a two non-vanishing equation instead of one. In the case of love wave, there was only one equation, non-vanishing equation, but here we are getting two. But what is the special observation in equation 45 and 46? It's a non-vanishing equation. Both are coupled. U and W, both are the coupled equation. One important property is to be kept in mind, that U is a horizontal component and W is a vertical component. Now, since it is following a elliptical path, so having both transversal and longitudinal component. Now, this basically gives an idea that whether, because it is following an elliptical path, it is having some sort of rotational nature. And since it is moving ahead also, so it is also having a longitudinal nature. Means, if we can think of a Helmholtz decomposition in this case, Helmholtz decomposition, a divergence free part and a curl free part. So if we assume U and W in the form of two potential functions called wave function phi and psi, we can just decouple this equation 45 and 46. How? If we substitute this 47 in 45 and 46, we will finally able to, from 45 we will be getting 48, and from 46 we will be able to get 49. If you simply observe this particular quantity with respect to x, this quantity with respect to z, and this is simply 0, provided this is equal to 0. So phi, and what is that? Del square, it's a Laplacian operator of two dimension. So it's del 2 del x2 plus del 2 del z2. There is no del y2, because already being assumed that del y is not equal to, is basically identically 0. It's no quantities are going to be varying depending on y. So there is no partial derivative appearing in terms of that. So if we assume this, we will just get these two equations, and from these two equations we will get 50 and 50. Now we have to solve this phi and psi from 50 and 51. Again, we have to think of the propagation characteristic of Rayleigh wave. We have already seen that what is the pattern of its particle motion. But what is the pattern of its wave motion? Which kind of wave it is? If we just assume something which is related to that, may get this equation solved. So what is that? Here C1 is lambda plus 2 mu by rho, and C2 is mu by rho. If you see here C1 and C2, which one is higher than, which is higher, C1 or C2? Which one is higher? Which one is higher here? This C1 is higher. Okay. I think annotation should be stopped. There are some annotations being inbuilt. Okay. Leave it. So these are the C1 and C2. Now, if we have to solve it, what needs to be done? We are assuming phi and psi to solve those equations. Now we know that phi and psi are one correspond to the dilatational nature, one correspond to distortion nature, both are perpendicular. So we know that phi and sine and cos having a 90-degree phase difference. So we can consider sine in one and cosine in another. And this xi1 and xi2 are nothing but they are the amplitudes of those. Now P is a wave number and C3 is the phase velocity. Now if you have to solve this, if we consider it, if we just substitute this in the equations, which equations? 50 and 51. 50 and 51, for solving 50 and 51, we have assumed the solution like this because of the nature of the Rayleigh wave. It's progressive, it's harmonic, and it is having two components, and those components are simply perpendicular to each other. So if we solve 52, means if we solve that equation with help of 52, we are going to get this 54. So here what we are going to get, C3 is less than C1. C3 is the velocity of Rayleigh wave and C1 is the velocity lambda under root lambda plus 2 mu by rho. Okay, so we got one thing, because to make this particular square root real, we need this condition. That's fine. Now solving the another one. So this is the solution. Why we again here, if you see that we are considering only the negative exponential function. Why? Because this Rayleigh wave again dies out with respect to depth, and if we get the phi as like this. Now our aim is to solve for this psi. We have solved for phi till now. We have solved for 50, equation 50. Now we will solve for 51. To solve for 51, we need to consider this 53, and we will lead to again ODE of this form. And for this to be real, we need to have C3 less than C2. So what a special thing we are getting, that the phase velocity of Rayleigh wave is less than the lambda plus 2 mu by rho, square root of that, and mu by rho. So we know that out of C1 and C2, C1 is larger and C2 is smaller. So your Rayleigh wave is lesser than the C2. But how much less? That is the question. So we know that C1 and C2 are nothing but those are corresponding to the P wave speed and the S wave speed for the isotropic medium. So Rayleigh wave is lesser than P wave and speed. Rayleigh wave speed is lesser than P wave and S wave. That is okay. That is well accepted. But how much it is lesser than S wave? That is a question. If we can get something on it, something more precise, it will be helpful. So now the solution of 56 we are getting like 57. So we got 55 and 57 with us. Now we will see what are the boundary conditions in this case. The boundary conditions, we know that here in the case of semi-infinite medium, there is only top surface, and that is basically stress-free. What is that stress-free condition? That the tractions, we have already seen that for any particular surface, there are three stresses, 3 tractions. One is normal and 2 are tangential, 2 are shear. So here in this case, those stresses which are going to contribute towards the boundary condition are tau zz and tau xz. Tau zz is the normal one, tau xz is shear one. Now we already know that tau zz and tau xz in terms of displacement, and we know that displacement is being decomposed, u and w is decomposed in terms of phi and psi, and those is being substituted here, and finally we basically get this equation 60 and 61 with help of solution and the boundary condition. From these two equations, if we eliminate this arbitrary constant, we are able to get this. And if we further solve, we will get an equation like this. It's a cubic equation in alpha 1 square. So 6 roots are possible. We are trying to find the value of alpha 1. What is our alpha 1 here? Alpha 1 is C3 by C2. C3 is the velocity of Rayleigh wave, and C2 is nothing but it's simply the bulk shear wave velocity. Bulk shear wave velocity is less than the bulk dilatational wave velocity, and that is lambda plus 2 mu by. So just we need to find this alpha 1 value, and we are getting a 6-degree polynomial equation in alpha 1. We have just tried to see, and this alpha 2 is known quantity. This is C2 by C1, and this quantity is less than 1. Why? Because C1 is lambda plus 2 mu by rho, and C2 square is mu by rho. So that is less than 1. So we calculated F0, which is coming out as negative because alpha 2 is less than 1. So finally it is a negative quantity, F1 is positive quantity. So definitely a root will be lying in 0 and 1. And we are interested in 0 and 1 because we know that Rayleigh wave speed is both lesser than C2 and lesser than C1. So how much C3 by C1 or C3 by C2 is, that is between 0 and 1, but what it is, we are very much interested. That's why we have checked in 0 and 1 interval. And now to get exact value, we are considering that Poisson ratio for the medium as 0.25. For this particular Poisson's ratio, what we have, for this particular Poisson's ratio, our lambda and mu, both the stiffness constant becomes the same. And we get all 6 root as like this. But we are interested in those root which are in 0 and 1. And that is being obtained by the plus of under root 2 minus 2, 3. So C3 upon C2 is going to be plus under root 2 minus 2 upon root 3, and that is 0.919, and which can be written as like this. So what you can see, that Rayleigh wave speed is 91.94%, 91.94% of shear wave speed of the medium. And that is one important result of this. So Rayleigh wave speed is lesser than both longitudinal, we can say longitudinal speed, dilatational speed, and distortional speed of the 3-dimensional waves propagating that interior. So this is the one important property of Rayleigh wave, and again it is going to be very much useful in different non-destructive testings and other particular testings, you can say, or in different exploration sectors it is being used. So this is all about the Love wave and Rayleigh wave modeling, where we can see that yes, differential equation comes into the picture. This the case which is being taken up is the simplest one by dealing with the isotropic homogeneous material medium. if we keep on increasing the complexity, will give rise to definitely the more complicated problem, which is going to be contributing to the present state. Okay. So this is all from my side. So thank you very much for your patience here. Thank you. So I'm now open up for the questions, please.
Thank you so much, sir. That was very thought-provoking and visually comprehensive presentation. We appreciate that. We'd like to open it for question and answer. If anybody has any question, they can unmute themselves and ask the resource person directly, or they can otherwise leave it in the comment box and we'll read it out. Any comment, any insight, anything?
Good evening, sir.
Yeah, good evening.
Sir, you discussed about the isotropic median. I wanted to ask whether or not we can classify or consider dry sandy median as isotropic.
Actually, yeah, that's a good question. Dry sandy medium as isotropic. Actually, the first thing is that in dry sandy medium, basically the number of stiffness constants are two, Lam's constant, lambda and mu. But if you see that associated with the shear modulus, we are getting one eta appearing, and the value of eta is greater than equal to 1. If it is going to be 1, it's going to be completely isotropic, elastic medium. But if we introduce that eta, you are going to have the shear modulus affected. So of course there are two constants only, but because of the presence of eta, you are going to have that shear modulus vary, right? And you know that because of the sandiness, the most effect is going to be on shear forces, shear stresses. And that's why it's basically associated with the mu. So this is the main intuition why the sandiness is being considered, and it is considered to be isotropic but with a small fluctuation. So if you consider in terms of symmetry, of course it is isotropic, but if you take it as you can say the completely isotropic medium, but you can say that yes, because of one parametric effect, we are not actually lying in the domain of isotropic. So it's something you can say in between.
Okay, thank you so much, sir.
Thank you, sir. Anybody else? As I do not see any questions incoming, I would like to request Dr. Ajit Kumar Singh from College of Post-Harvest and Technology, to offer formal vote of thanks.
Good evening, sir. On behalf of organizing committee, I take this opportunity to extend my heartfelt thanks to Professor Abhishek Kumar Singh for his lecture. Your valuable insight on the role of differential equation in seismological modeling have broadened our understanding and will certainly guide us in our academic and research. Thank you once again, sir. With this, we come to the conclusion of the fourth day of the FDP. We sincerely thanks both our speakers for their enriching contribution and our participants for active involvement. We look forward to welcoming you all again to another day of learning. Thank you so much, sir.
Thank you, Dr. Ajit. Thank you for having me. It's my pleasure.
Thank you so much. Thank you and have a pleasant evening ahead. Thank you all.
May I leave, Ajit? May I leave now?
With this, we conclude today's program, and we look forward to having you all tomorrow. Thank you and have a good evening.